Welcome to the fourth session. Now, I know that this being the fourth one, we've had a pretty good introduction to WisML, but I'm just going to super quick make sure that we're all on the same page of what we're talking about, right? So, what is WisML? A domain-specific language for automating big ML workflows. That's like the elevator pitch for what WisML would be. And just looking at that sentence, we break it down. We say, okay, well, what is a domain-specific language, and why did we do that? And that we covered that fairly well, right? Talking about this being a Lisp-style language that has machine learning operations as first-class citizens, and we talked a lot about the motivation of why we did it. And what do we mean by automating, right? This could be lots of different things. Actually, let me not dive into that too much. And then, of course, what is a workflow? And what we've seen is, right, the DSL gives us maximum flexibility, right? You have a full programming language. It's binding agnostic, right? You're actually able, this is very important, you're actually able to abstract the machine learning piece of a predictive application that you're making and write it once and reuse it in any binding. Okay, so now as you're making a dashboard for a full stack predictive application, if you will, the machine learning piece doesn't have to be re-engineered if you decide to change the language, right? It's optimized for the cloud, meaning that if you have a subscription level, it can run 8 tasks in parallel, and it'll run 8 tasks in parallel for you, and it'll handle all of that parallelization, and you don't have all these REST calls going back and forth to the cloud. So what do we mean by automating? Well, this kind of wraps in all the other things that WisML gives us for free, sort of like the bonus features, if you will. You get the ability to create easy, repeatable tasks. You get the ability to create workflows that are easy to share, right? I can put them in a gallery. I can create secret links. They become atomic execution units that are shareable on their own. I can put them directly into the UI and do one-click executions, and I can do all of this through the API as well. So these become, again, these little execution units that I can run with an API call. All right, and then we spent the last 2 sessions talking about what exactly is a big ML workflow. We've seen that, of course, it can just be a series of machine learning steps. They can be something more programmatic, okay, like doing a cross-validation, or we can even, as Charlie was showing us yesterday, we can even build higher-level machine learning algorithms. Okay, how is this? What's happening here? What's going on? So WisML covers a lot of bases, and the important thing to keep in mind is that WisML is concerned with the coordination of resources inside the BigML platform. All right, so we've got all these sources and data sets and correlations, and WisML is all about bringing them together into these multi-step workflows. All right, and there's lots of ways you can put these resources together into a workflow. And so I actually tried to make a map. It's a very high level, but the basic idea is if you think about all of the ways that the resources connect together in BigML, then you get something that looks kind of like this, right? A source always becomes a data set. Data sets can be used, they're fundamental, that's why I put them in the middle. They can be used to do all the supervised learning, that's sort of in the upper left hand there, and all the unsupervised learning, the upper right, right, the clustering, anomaly detection, association discovery. You can use, once you've built one of those models, you can then use a data set to do batch scoring, right? So batch prediction, batch anomaly, and that process actually outputs a data set again. And then we even have some statistical tests for data discovery and correlations. And then we also have Flatline, which is actually another domain-specific language that we have that lets you do feature engineering and programmatic transformations, and this converts data sets into data sets. Okay, so this is the way these resources can be put together using WisML. And then we've already kind of started to see what you can do with this, right? So one thing you can do is you can start talking about optimization processes. And so these are examples that we saw. You could build a workflow that tells you whether or not a model or ensemble is the best to use for your particular data set. It's probably the ensemble, but every now and then it could be the model, right? But this is now a basis for an idea that you could extend. If further in the optimization category, we saw an example with best first features. Maybe I've got 100 features and I just want to find the 10 best. All right, so now I can now create, using WisML, a workflow that puts together the resources in BigML to create an algorithm that will help me determine what the best first features are. And then we can extend that even further to Smackdown, where we can say, okay, I want to use an ensemble, and there's lots of ways I can parameterize an ensemble, number of trees, how many nodes are in each tree, how many trees to use, whether or not random forest or bagging, and there's lots of things I can control, and Smackdown will go through and find the optimum parameter set to build the best possible ensemble for your particular data. Yeah, but then we also saw, of course, that you could build these sort of higher level algorithms, right? So we saw an example of stack generalization where we actually build sort of a meta algorithm based on models and ensembles, perhaps logistic regression as well. But you take all these basic predictors and then you put them together with a second level predictor. We saw an example with gradient boosting where we're making an algorithm that essentially measures the error in a tree and then corrects the error. And then I put cross-validation on there as well, which is also in the gallery. So you can do cross-validation as well. If you think about the BigML platform right now, we have evaluations in the workflow, and then a cross-validation is essentially a set of evaluations where you take your data set, you split it into k pieces, and you build with k minus 1 and use the last one to make an evaluation. Then you just kind of mix that up into all the possible permutations. Well, that's something that is very clearly a WisML workflow, right? Once you have a basic evaluation unit, like we do, you can now create a workflow that does a cross-validation, and so we've provided one of those. Okay, and then for today, what I want to talk about is sort of the two that are in the bottom left-hand corner. And one is you can use WisML for transformations. Now, first, this might seem somewhat counterintuitive, but you can create, there are certain data transformations that operate like workflows. And one in particular is that I end up playing with a lot, and I'll show an example or two today, is this idea of flatline wrappers. So with flatline, you can do this feature engineering, and that's super powerful, but it becomes, if it's a transformation you're doing a lot, WisML lets you turn that into a one-click operation. So now it becomes something that every time I have a data set of a particular type, and if I want to make a transformation, like I have a date, maybe I have a date field, and I want to know the phase of the moon, right? I can write a flatline transformation that turns a date into the phase of the moon, but with WisML, I can now make that a one-click operation. And anytime I have a data set that has a date field in it, I can just click a button and extend that data set automatically with the phase of the moon. All right, so it allows me to sort of wrap these, or it doesn't sort of, it exactly allows me to wrap these flatline expressions into an executable unit, which makes them very powerful. Another example of a transformation, which is one of the scripts that we provide, is removing anomalies, right? So I take a data set, build an anomaly detector, take out the top 10, or the top n anomalies, I should say, and then use that data set to further build my model. And this is an example I like doing with the diabetes data set we have, because you have these top 2 anomalies. When you take them out, all of the evaluation metrics go up by 3%. All right, and then the other side is more of what you can, of workflow types, is things that are domain specific, right? These are very, depend on what you're doing. And so one clearly is creating an application workflow. So it's very unusual that you are solving a predictive application problem and you take your source and you make a data set, you build a model, and you're done, right? There tends to be a lot of transformations and filtering and bringing two things together, maybe doing a batch prediction. There's a lot of steps in there, and when you build that workflow, it's nice to be able to automate it with WisML so that it becomes something that's easy to repeat, especially if it's a workflow that you're going to be doing very common. Now, of course, this is domain specific. It's about building a specific application, and then this could be abstracted just to any repetitive task, something that you're doing over and over and over that involves multiple steps using BigML resources. And now you can create a WisML script that allows you to execute these repetitive tasks without having to do them one at a time, or one API call at a time. Okay, so let's take an example. So there's a site called Redfin. It's a bit like Zillow or any of these other real estate pricing websites that allow you to search for, actually let me just show you what Redfin looks like. That allow you to search for real estate. So this is Corvallis. This is where the BigML headquarters are, and actually where I live as well. And you can put a city in, filtering. For example, right now I have only houses selected, and I'm looking at sale records for the last year. And what's actually kind of cool about this is that they have all these parameters for these houses, number of bedrooms, number of baths, square footage, etc. And as long as you have less than 500, you can actually scroll down to the bottom here and click download all, and it kicks out a CSV for you. And this, of course, now becomes something that we can play with in BigML. So what are we going to do with this? Well, one idea I had was, if I have the data for sold homes, which you see on the left hand there, these are houses that have come onto the market and then they sold, right? So I know how much they sold for. That means I could build a model that looks at the parameters of a home in a specific city and tries to predict the price. And then I could take, on the right-hand side, all of the houses that are currently for sale. They haven't sold yet, but they have a list price. It's what the owner is asking for. And I can now make predictions for what their sale price will be, and I can compare that list to the prediction, and I can now look at the difference and see, I can find examples of real estate that might be a deal, or maybe examples of real estate where the owner is clearly delirious, right? However I end up using that information, it's something that we could build very nicely, and maybe if I am looking to invest in houses, I would be looking for ones that are I predict would sell for much higher than they're listed at. That might be something I want to look into. Okay, so I'm going to do this workflow by hand to give you a flavor of what it actually looks like, and then we'll automate it. Okay, so first I have two sources I need to bring in, and I've already downloaded those from the Redfin site, so I'll pull those in. So these are the for sale and the sold homes in Corvallis. All right, we'll start with the sold homes. All right, these are houses in Corvallis that were sold over the last year. Now, of course, we could use more, but I'm using a small CSV, so this goes quickly, and also it's much easier to download, only 500. And this will give us a sense of the parameters that Redfin gives us. Okay, so we can see the sale type. In this case, these are all past sale. I filtered for only single-family residences. We have an address, a city, a state, and a zip code, and then we have what the house was listed for. And of course, further down, these being homes that were sold, we have a last sale price. I went scooting right by it. Here it is, last sale price. Because these homes were recently sold, this is what they most recently sold for. And the date that it was sold on, so these should all be in 2015. And you can see there's a lot of features in here that probably aren't going to be very useful, or at least aren't for the application that I proposed, right? I don't really care about whether it was a short sale or whether it ever had a reduce in price. I'm not particularly concerned about the date that it was sold. There's a lot of the open houses. I don't know. I don't need all this stuff. So when I go to build my data set, I'm going to leave a lot of this out. I'm going to filter it. So what I can do from this CSV is I configure my data set and take some of these out. So I can take this out because it's the same for all of them. It's the same. The address might be interesting. We'll leave that. We'll take out the city and state and zip because those are all the same. Now the list price, these are homes that are sold. Actually, for the sold homes, I don't care what they listed it for. I mean, that'd be something that we could look at. But this is in the past. I only care what it's sold for, so we'll take that one out. And we will leave the bedrooms and bathrooms and location. These are all perfect. Square footage, lot size, year built, all good. I'm not concerned with how long it was on the market. Again, I'm not concerned with any of these features. I don't even care about the original list price, but I do care about the last sale price. This is the thing we're going to predict. And we'll take out all of these. None of these are particularly interesting right now. Latitude and longitude we'll leave in, right, because these are features that could very well correlate to the value of a home. Lots of cities have geographic locations that are worth more or less. And we'll take out the is short sale, and then we'll let that build. Okay, so I'm just starting from the CSV, and when I build the data set, I'm just leaving some of the features out that I know I'm not going to be particularly interested in. And while that's building, let's go ahead and do the for sale as well. So I'm going to create this data set, and we're going to do the same kind of thing. Now, these are the homes that I'm going to make a prediction on and compare to their list price. So now I do care about their list price. So, but again, we'll leave these out. City, state, and zip, those go. So I need the list price this time. Beds, baths, location, square feet, year built, parking spots, days on market, no, status, not concerned. These all go, bye-bye. Okay, I'm not worried about the original list price. And you can see these newer homes are not going to have a last sale date. Some of these are older and have been sold more than once. But again, this time, instead of the last sale price, I'm interested in the list price, right? Because I want to compare that to the predicted. We'll take out these guys, all go, and this all goes. Latitude, longitude is short, perfect. Okay. All right, so now I've got my two data sets. Okay, so again, just to review, I've got two data sets. I want to build a model with this one, and then I want to use that model to score all the homes that are in this one. So let's go ahead and do that. Let's build a model of houses that are for sale. So I'll configure my model. I don't want to predict the longitude. I want to predict the last sale price. Okay, that's the thing I want to predict. And we'll go ahead and leave all of the features in, and we'll just take the defaults for this. All right, and we end up with our tree, and we can look at how it's making its decisions, right? So we can see it's making a decision based on square footage at the root of the tree. That sort of matches our intuition, right? We expect the size of the house to be related to the sale price, so that's good news. And we see the split we have is around 2,000 square feet. and we can get a sense of the, as we go down the tree, we can look at some of these rules that we're discovering. Okay, so here we have very expensive homes. Okay, almost $1 million. But we can see, okay, it's a very large house, more than 3,800 square feet. It's in a certain latitude and has much more than 4 3/4 bathrooms. All right, perfect. So let's take this model now and use it to score all the homes that are for sale. So to do that, we're going to do a batch prediction. All right, and we're going to use the model we just built and the for sale homes. Okay, now the output of this, so it's going to take everything in this for sale data set here, and it's going to run it through the model and score it. And we're going to get out is all the features of the home plus a predicted last sale price. I don't want to call it predicted last sale price. I want to call it predicted price, perhaps. So the output column we'll call predicted price. All right. So now we can see what this looks like. I get all of the features of the homes that are currently for sale, plus I get a predicted price. All right. So let's let that run. Okay, here's my output. I want to create a data set from this. So now I have all the homes that are for sale. I have their list price here, and I have their predicted price, what I think they're actually going to sell for. And now to compare these nicely, I want to take the difference of those, right? If I take, for example, if I take the list price and subtract the predicted price, then if that's negative, that means I'm predicting they'll sell more than it's listed for, so it's potentially a deal. So let's engineer a new feature in this data set. We can do that with an add field, and we'll call this deal or something. And for this, we'll go ahead and use a Lisp expression. So now I'm using a flatline transformation. And what I'm going to do is take the difference of the field list price and the field predicted price. And just to make sure I didn't make any typos, we can validate this expression using this expression editor. So flatline editor, I can see this expression is valid. I can make a little preview. All right, so I can look at this first house here as a list price of 500,000 or so, and it has a predicted price of 465, and I can see that the deal value is 30,000. So I can see this is I'm predicting a slightly lower price than what it's listed at, right? So it's a positive number. Let's go ahead and accept that and let it create. And we're there. Now I have a data set of homes that are for sale, and I have some values. I can see negative numbers, so these are potentially homes that might be a good deal, all right? And I can see positive numbers. These are homeowners that as I alluded to earlier, are perhaps delusional about how much they can sell their house, or perhaps they have characteristics that aren't being captured in these parameters, and that would be something we could investigate. That might justify its value over what the model predicts. Okay, so now let's assume that I would like to run that again for a city that's nearby called Albany. I don't want to have to do that whole set of steps every time, right? Making the data set, unchecking all the features, building the model, do the batch prediction, creating the output data set. I don't want to do that again. So let's make a workflow to do this. And just to put it pictorially, this is what that workflow looks like. We took our sold homes, we filtered them. The new features we didn't actually do, but we're going to do it in a minute, so I included it in the chart. And then we used that to build a model, and then we did the same thing for sale. We filtered, and then we used that to make a batch prediction, which outputted a data set, and then we did one more transformation to create our deals data set. Okay, so to translate this into WisML, it helps to think about the pieces that are repeatable, right? So we can kind of see those two are basically the same thing, right? I'm just taking a source, I'm making a data set in a very specific way, and ultimately, when we do our transformation later, I'm making new features in the same way, okay? And then at the end here, I had a flatline transformation I did. There's a very specific use case. And then in the middle, what I'm left with is a very straightforward, create a model, create a batch prediction, output as a data set, all right? And so now that I see these pieces, I can code each one in WisML. So let's do that. Out of here. And I'm not actually going to type in the WisML, of course. So let me show you the URL. So I have in my GitHub gist. Here we go. I have quite a few little WisML examples, and this one is the one that I've called Redfin Deals. And as you may recall from the prior day presentation, when you share these WisML scripts in a gist, you can create two files, one called the JSON and one called the WisML. So this is the actual WisML workflow script. And the JSON defines all the inputs and outputs so that when I import this, it'll import very nicely. It will know exactly what parameters are expected for inputs and outputs. So let's go ahead and import this. So I'll copy the URL. We'll go up to our WisML scripts. And now I want to import a script from GitHub. I can just paste my gist in there, and it should pull it in. And again, you can see now the inputs and outputs are all defined nicely. Okay, so I can see it takes two sources and outputs a data set, which is kind of what we expected. So let's take a little dive into the code here. I'll show you exactly what's happening. All right, I think I can make this maybe a little bigger. That'll help. Okay, so remember I had in the top two halves of this picture, we have the two workflow pieces in green there. They're essentially the same. Well, that's this first function right here. I called it the Redfin data set. Okay, so I'm making a data set specific to Redfin data. Okay, so I'm defining a function called Redfin data set. It takes as input a source ID and a list of fields. So these are the fields that I want to include in the data set from the source. All right, and then all we're going to do is kick off a let. And inside here, I'm going to define the data set. I'm going to define something called the data set, which is the create and wait data set. So this is our machine learning function. All right, and it takes a parameter, which is in WisML is a map type. And this looks just like the API call. Okay, if you're familiar with, for example, using the REST API directly, or if you've been using Python bindings, you know that you would call the create dataset endpoint, and you would pass it a JSON object that contains, for example, the key source, which tells it what source to build the dataset from. And in this case, we're also going to tell it the input fields and pass it a list of fields. Okay, so we can see here that this function is expecting fields to be a list, and it's just going to pass it straight through to dataset. All right, now outside of this let, all I'm doing is returning the data set that I just created. Now that looks a little bit crazy, right? I mean, I could just get rid of the whole let and I could just do this create wait data set, return it, but I'm going to do a transformation later, so I've just left that as a placeholder so that inside the let I can do one more step and it'll all make sense. Okay, so this next little function, this is the bit that was in green. If we look here, or the blue, sorry, it's the deals data set. Okay, so remember what we did is we wrote a flatline transformation that subtracted two columns. And so this is a little piece of WisML that repeats that. All right, so I'm defining a function called column A minus column B. And remember, as Charlie was describing, you can have these lots of valid characters in a function name. In this case, I have a dash in my function name. That's fine. So this WisML function is called column A minus column B. It takes as input a dataset ID. Okay, so it needs to know what dataset it's transforming. And then it takes two inputs, column A and column B. Okay, these are going to be the names of the columns that we're going to take the difference of. And then all this function is going to do is create and wait a create a data set. And this time we're creating a data set from a data set. And if you look in the API documentation, the way you do that is you, instead of passing the source to create a data set from, you just pass it an origin data set. All right, this creates a data set from a data set. And then we have, in exactly the same way you would do again with the REST API or with the bindings, we pass a parameter called new fields, and this is a list. And inside here we pass a little set of maps, and each map is a field that we want to add. Okay, and I'm passing two parameters that define this new field. One is the name of the field, all right, and here we're using the WisML string constructor, which just takes a list of things. Well, it's not a WisML list, but it is a list of things, and puts them together into a string. So it's going to take the name of column A, it's going to take the string space dash space, and the name of column B, and it concatenates them all together into a string. That will become the name of the column that we're engineering in our data set, our new feature. And then we pass it the field, which defines how this field is being created. All right, now here we can see an example of using flatline inside WisML. So what this expression does is it takes all of these strings that occur after it and treats it as a flatline expression. All right, so we can see exactly the same thing that I typed into the flatline editor. Okay, we're taking the difference of the field column A that you tell me and the field column B that you tell me. And you'll notice that column A is in these double squiggle braces. And what happens inside this flatline operator is that those become a quote. Okay, so when WYSML evaluates this flatline expression, or creates a flatline expression for flatline to evaluate, it will actually pass in a quote and then the name of column A and then a quote. The same way when I typed it in, I put the field name in quotes. All right, and that's it. So we're just defining a function that takes an input as a data set, the name of two columns, creates an output data set that has this flatline transformation in it, which computes the difference of those two columns. Easy. Okay, so now we're ready for the meat and potatoes, and it looks a little uglier than it actually is, so don't be frightened. So this next block is this centerpiece, all right, the part that isn't highlighted. That's what we're going to be looking at. And we're calling this the Redfin deals. That's the name of this WYSML function. And we're just going to pass as input two sources. One is the sold source and one is the for sale source. Easy. Okay, so we kick it off with a let, and we're making something called default fields. So this is the list of fields that both data sets used, all right? So they both used the address, the beds, the baths, location, et cetera, et cetera. As you may recall, the only thing that was different between them was one had the list price and one had the last sale price. Okay, but these are the fields that are common between both data sets that we need to create. And then for convenience, I'm just defining the three fields that we're interested in, all right? One is the for sale field, which is called list price. Okay, that's the name of the field in the for sale data set that we kept. And we have the last sale price, which is the name of the feature in the sold source that we kept. And then remember when I did the batch output, I wanted to call the field that we were predicting, I wanted to call it the predicted price. Okay, so I'm just defining those as placeholders. And then we make the for sale data set. All right, we do this by calling the Redfin dataset function above. That's up here. Okay, and we pass it the for sale source, right? Because remember, Redfin dataset, the function we defined, it just needs a source and a list of fields. And now we use the WYSML function append, which will take the list default fields that we just defined right up here, and pass also the for sale field. Okay, so this little WYSML function is going to take this list. It's going to append the name of the for sale field, and then pass that as a list of fields for the Redfin dataset. And boom, what comes out of there will be the dataset, and we're assigning that to the for sale dataset. All right? And we do the exact same thing to make the sold dataset. Okay, we call the same Redfin dataset function, but with the sold source, and this time we take the default fields and add the name of the sold field, exactly the way I did it manually. Okay, once we do that, we're ready to build the model. Okay, so now we're in the middle of that workflow picture I showed you. So we're going to define something we're going to call it the sold model. And it's going to be a machine learning function, create and wait model. And then just like an API call, we need to pass it a map that contains the information about how to make this model. And so in this particular case, we pass it the data set key and the data set identifier. In this case, we were modeling the sold data set. And we need to tell it what to predict, right? And then the same way when I did configure model, I chose the objective in the little drop down on the left-hand side. I need to tell it to predict the sold field, okay, which again, remember, is the last sale price. Perfect. All right, once we had the tree, then we did the batch prediction, right? So that's the same thing. We're going to call this the sold batch prediction. And this will be a machine learning function, create and wait batch prediction, okay? And again, just like the API, we need to pass it the map that contains the parameters that define how to make this batch prediction. And in this case, what we're going to do is tell it the model to use. So the model is the one we just built right there. It's the sold model. We're going to tell it what data set to score against the model, which in this case is the for sale data set. All right, telling it all fields, just make sure that all of the fields in the for sale data set get in the output, so we have all the same parameters for the houses. We can define the prediction name, so this is the name of the predicted column, in other words, the name of the values that are coming from the tree. In this case, that's predicted field. And then output data set just makes sure that when we run this batch prediction that we get a data set as an output. Okay, so now we've created both data sets, we created the model, we created the batch prediction. Now we have a little bit of a snag here because in order to proceed to the next step to do the flatline transformation, I need to know what the data set was that got outputted, created by this batch prediction. All right, and what I have instead is I have a batch prediction. This sold batch prediction that we just defined is a batch prediction. It's not the data set it created. Okay, it's exactly like if I go back to the dashboard, just so I'm crystal clear what I'm talking about here. If I go back to predictions and batch predictions, so here's my batch prediction. Okay, this is the batch prediction. It's not the output data set. So I need to know what the identifier of the data set that was created as an output of this batch prediction. All right. Now, you may have noticed when you're working in the UI, there's this little gear icon up here, and if I click on that, it actually gives me a link to the API endpoint that defines this batch prediction. Okay, so this batch prediction is in the API is represented as a JSON document that tells you everything about how it was created. All right, so I can see, for example, that the all fields parameter was true. I can see when it was created. I can see the data set that was used. I should be able to see the model that was used. Okay, these are all the things about this batch prediction. And one of the things that I'm interested in is the fact that there's this output data set resource. Now, this is the data set that it created as an output of this batch prediction. That's what I need. I need this data set identifier. That's the piece I need. All right? So that is what's happening in the script here. This next step, I'm defining the batch prediction data set. All right, now what I have is the batch prediction, so I fetch it. Okay, and this WSML call fetch takes an identifier and returns the map, okay, that represents an object. So in the same way I just showed you this JSON object, all right, this is what fetch is going to return. It's going to take what starts as just the identifier, like this batch prediction up here in the URL, and turns it into this map. All right, it's going to fetch that object. And once I have it, I can use the WSML function called get, all right, which is going to look for a key inside here and return the value. And in this case, the key I want is the output data set resource, exactly like in here. This is the output data set resource. It's going to look up that value and return that data set string, which is exactly what I want. All right, so we fetch the batch prediction, which gives us a map. We use the get call with this key, and that is the batch prediction data set output. Okay, now we're there. We're at the last step. So you can see I have a parenthesis here that closes the let. It's a little hard to tell, but if I put the cursor right there, I can see there's a little bit of highlighting on that parenthesis there. All right, so I've just closed all the defines inside the let. And so I'm making the last call inside here, which is I'm calling the column A minus column B function that we defined above. And remember that it takes as input a data set and the name of two fields that we want to take the difference of. And you'll notice that for the data set, I'm not just passing the batch prediction data set, I'm passing this wait forever on batch prediction data set. Now, why am I doing that? Well, this is an asynchronous platform, all right? And so when this step happens right here, when I create this batch prediction, this basically starts a process that creates the batch prediction, and then this script is going to continue on. It's going to go down here, it's going to find that field, it's going to go down here, and it's going to do this. So it's going to do all these steps before the batch prediction might even be done, right? I mean, it could get queued. It could take a second or two, or maybe it could take 30 seconds. I don't know. And so all I'm doing here is I'm just making sure that this batch prediction is ready, okay, that this batch prediction data set is ready, I should say. So wait forever just makes sure that that resource is done. And the output of wait forever is the identifier itself. So I'm just passing this data set, and I know its status is done, and then I pass it the name of the two fields, right? For sale and predicted. So this will take the list price minus the predicted price. All right, and that's it. So the last thing I need to do is have this little stub down here, which is going to define the inputs and outputs. Okay, so I'm going to define something called the Redfin deals data set, and it's going to call this Redfin deals function that we just defined right here, Redfin deals. Okay, and it's going to pass it the Redfin sold source and the Redfin for sale source. Okay, this is basically just defining the inputs and outputs, and then we can see they're all down here. They're exactly the same. There's the Redfin sold source, the Redfin for sale source, and what we get out of it is this Redfin deals data set. All right, let's try running it. Okay, so now I imported it from GitHub. I was showing you in the script editor what the script looked like, and then I submitted it. So now this script exists in my account. When I do that, it immediately goes to the execution step. Okay, so it just handed us over to the execution step where we could run it. So let's try running it. So for the sold source, we just need to use this one. And for the for sale source, we just need to use that one. And then we hit execute. Okay, so now rather than what I did before, going through the UI one at a time, I can just now run this workflow as many times as I want. All right, so I can see it created 3 data sets, it created a batch prediction and a model, and here's the output data set that it created. And if I click on this, I have exactly the same thing. Here are the homes that are for sale. They have a list price, and here's the list price minus the predicted price. We should see a similar range here, right? Minus 600 or so up to 429. All right, so if I want to do this again, maybe I want to do this for Albany, which is a city nearby. Okay, I can actually take 2 new sources. I can upload those ones, and I can go back to my script, and here's my Redfin deal execution, or sorry, Redfin deals script, and I can just run it again. I can say, okay, now let's run this one for Albany now. For sale, boom. I've just run my workflow to find potential real estate deals in a completely another city. All right. Here's my output data set. And same kind of thing. All right. So now I can just run this workflow as many times as I want for different cities. So very easy now. Okay. So let's talk about transformation workflows. Remember I was saying that the 2 things I wanted to focus on was one was this idea of a predictive application workflow. It's what I just showed you with doing that Redfin deals, right? It's an idea I had for how I could predict or I could look for real estate deals. And I designed this workflow in the UI, and then I was like, oh, I need to make this WYSML script. And then the lower left-hand column, I was telling you that you can do these like flatline wrappers. Okay, and we sort of saw an example there where I did that flatline transformation deals at the end. But the basic idea is anytime you're using a flatline transformation to turn a data set into an extended data set, you can turn it into a WYSML script that makes it very nice. Okay, that makes it a little repeatable unit that is easy to apply to any data set. Okay, so let's take a look at an example. Okay, so if we go back to Redfin for a minute, and we look at the model that this thing built. All right, so we'll use the Corvallis one, that's fine. And what I want to do is I want to show you the field importance. Okay, this is in the model summary report. So one of the things that BigML does as it's building the model, it actually looks at how much each feature is producing the error, and it uses this information to create this little model summary. So it tells you how important each field was, basically, in predicting the output. All right, so I can see the square foot was a very dominant feature, and lot size and year built, those all sort of match our intuition. That's nice. And I can see latitude was actually pretty useful at nearly 5%. Now, I have this insight, okay, that latitude and longitude aren't really specific enough. Okay, they're telling me something about the location east, west, north, south, but cities have other features in them that make real estate more valuable. Like, is it close to the river? In the case of Corvallis, is it close to the university? All right, we have a university here called Oregon State University, and houses that are near it tend to sell for a lot more because investors buy them up and then turn them into rental properties. And since the university goes up by like 1,000 students every year right now, that's driving house prices near the university. So I have this idea that, you know, maybe if I had an extra feature in here, if I could engineer another feature that told me how far away it was from the university, then that might be something the model could learn from. Right now it might learn, okay, that houses that are near the university or far away affect the predicted price. But I have latitude and longitude. So what I need is a transformation that turns latitude and longitude from a reference point into a distance. Now, I've already written this. You can do this with something called the Haversine formula. Actually, there's a couple ways to do it, but one is Haversine. And this is a somewhat messy looking, where'd it go? Oh, a little slow on scrolling here, sorry. Here it is, lat long for reference for distance. And actually, let me just go ahead and import this. I'll show you in. So we'll go back to our scripts, and I'll import from GitHub again. Pull this one in. All right, and what we can see is that this is a little WYSML script that I wrote. It computes the distance between lat long coordinates and a reference point. All right, they have to be in sign degrees. Okay, so no north, west, south, east. They got to be negative, positive, and negative numbers. And we can see that really all it's doing is taking a whole bunch of inputs. All right, there's a lat long reference. This is the name of the function, sorry, lat long reference distance. That's the name of this function I'm defining. It takes as input a data set, a latitude field, a longitude field, a latitude reference, and a longitude reference. And then all it does is create a data set. The same way we did that deals transformation. It's you create a data set using an origin data set, the data set you passed in, and then it creates a new field, and it has this enormous flat line transformation. All right. Now you can see that if this is something I wanted to do often, that having this flatline transformation defined somewhere else or going into the editor and pasting it in would be somewhat tedious. I mean, this is a rather complex looking flatline transformation. I don't want to have to type this or paste it or whatever. I want to do that over and over. Okay. But by using WisML, I can now wrap this into this little execution unit that I can use over and over. That's very nice. And what we have then is this is done. So I can actually run this. I'll show you how this works. All right, so what we can do is take, for example, the Corvallis sold homes, let's say, and I need to tell it the name of the latitude field in the data set. In this case, that's actually latitude, and I need to tell it the name of the longitude field, and then I need a latitude reference point. Okay, in this case, I'm using the coordinates of Oregon State University, so latitude reference and a longitude reference. Okay. And now I can just execute it. And this is going to transform my sold data set and add this information to it. All right. So here's my new output data set. So it just applied that flatline transformation and ran it. So okay. So here we have the distance in meters that each of these homes defined by the latitude and longitude is from the center of Oregon State University. And so I can see that the closest is about 700 meters all the way out to 15 kilometers or so. All right. Now I want to use this in my Redfin deals data set, or I want to in this step right here, I want to do this I want to create new features here, top and bottom for both of these sources as part of the workflow. Okay, so rather than a script, let's turn this into a library. So I can actually go into this script, and what I'm going to do is take the source code, and I'll just copy it. That's no problem. And then we can go over to libraries, and I'll write a library using the editor, and I'll just paste that same source code in here. And now because it's a library, I don't need this little stub to define the inputs and outputs. I can just get rid of that. Okay, and now I have this lat long reference distance function, and I can click the validate button. It says it's valid. I can give this a name, lat long distance from a reference point, for example. All right, and we'll create this. Yes. And now I've taken this flatline transformation and turned it into a library. So now I can use this in other WisML scripts. So let's do that. Let's take my Redfin deals. So here I have a Redfin deal script that we created before, and I'm going to create a new script using this one because it's going to copy it and put me back into the editor so I can modify it. Okay, so here's the same Redfin deals, and now I want to bring this library in. Okay, so I've got this library we just created. I can just type it in there. It finds it. I click on that. And now I can see, okay, inside that library, lat long distance from a reference, that's the reference point's name, there's this WisML function called lat long ref distance, and here are the parameters. All right, well, that's excellent. So what I can do is I can just put this transformation right in here. So I can call lat long ref distance, and this time I'm going to use the data set that we just created there in the let as part of the create and wait data set call there. And the latitude field, so this is just the name, so we'll call this latitude, and the longitude field is just the name, longitude, and then we need the coordinates again, because this function is expecting the latitude reference point, so we'll add that, and then the longitude reference point. Now I'm hard coding this for Corvallis. Obviously, we could make this a little bit better by having these be parameters, and then when you run this Redfin deals data set, you would put in the coordinates of the reference point. But for this demonstration, this is sufficient. Okay, so this I need to. Let's see, what am I doing wrong here? I feel like I'm forgetting something. Maybe I need to do this. still likes it. Well, we'll see if that works. All right, and that's it. Let's try it. Okay, so now we can try running this again. We'll take the sold, and we'll take the for sale, and we'll let it run. And now it's going to do all the same steps it did before, except that in addition, it's going, when it creates the for sale data set and the sold data set, it's going to run that transformation that adds the distance from the center of the university. All right, and so we can actually look and see, this is the output data set, which is the actual deals. All right, and I can see the distance is part of this data set now. And I can see the values have changed, right? We've sort of tightened our range up a bit, okay, which at least in my mind makes me think that it's probably doing a slightly better job, right? Because you may recall the range here was minus 600 or so, now it's minus 300. All right, so we're getting a little, I think it feels like we're getting a little bit better information in predicting these home prices. And we can actually confirm that by going to the model and looking at the latest model that we just built, and looking at the model summary report again and seeing how well distance did. And we can see, yeah, it actually did. So distance had a 4% field importance, and we actually bumped latitude all the way down to 1%. Now, the reason why that would be is that Corvallis does have a bit of a topography in that the homes in the north tend to be worth more than the homes in the south. So I'd still expect some contribution from the latitude independent of the distance, but you can see the distance from the center of the campus is quite an important feature, more so than latitude and longitude individually. Okay, but again, what WisML allowed me to do was take that somewhat complicated looking flatline transformation and turn it into a repeatable execution unit that I made into a library, and then was very easy to include into my WisML. Okay. Now, before you get super carried away, I want to just give you sort of a 5-minute walkthrough on something that, because I got super carried away, and so it's easy to do. And this is nice because I think it really calls out, or really demonstrates the difference between flatline and WisML. So we're going to talk about it. So I wrote this little WisML transformation to do JSON extraction. All right. So if you have a JSON document, okay, and this actually came up because of a Kaggle competition called StumbleUpon, and it has inside there, it has this boilerplate, which is actually the raw content of a website, and it's actually a JSON document. And it turns out if you can extract the key value pairs, you could do a little bit better in the modeling, right? Because you have like the title is the key, and that's the title of the site, and you have the body, and then it's the body of the site. And I wanted to be able to extract this. I wanted to do it in BigML, so I thought, maybe I can do this with a WisML flatline, a wrapped flatline transformation. So I started playing with it, and here's my first simple idea. Okay, so for example, if I want to find the key foo in that little JSON document there, right, where foo is pointing to another dictionary, if you will, where bar represents Baz, then what I can do is I can just kind of cheat, right? I can just think about this like parsing strings. Okay, notice I didn't call this a JSON parser. This is JSON extraction because this is not a parser. All right, but I can just keep everything to the right of the key I'm looking for. All right, so I can just look for foo and just take everything to the right. I know there's going to be a key, it should be in quotes, and there'll be a colon, so I can just strip everything to the right, and I would get what's left there. And then I can look at the first character of what's left, and if it's a left curly brace, then I can just look for a right curly brace. If it's a left square brace, then I can look for a right square brace. If it's a quote, then look for the end quote. Otherwise, just look for white space, like might be a rounded number. And what I get is exactly what I want. I get this little piece that comes out that's the dictionary that foo pointed to. All right, that's perfect. And this actually works pretty well. But of course, this is not entirely perfect, right? And I can give you a very quick example of this. So we can actually take, let me do this, sources. So we'll go up a folder, and here, I've actually got this StumbleUpon data set here, and while that's uploading, go over to the scripts, and I'll show you the JSON. Where'd it go? Simple. So this WisML wrapped function is somewhat frightening. We're not going to dive into that. And I want to create a new script. I'll import this one. Load it. Okay, so what this does, it takes input a data set, the name of the column that has the JSON in it, and the key you want to extract. All right, so I'll and it outputs a data set that's extended with the key that it extracted. So here's that StumbleUpon data set I was telling you about. I'll just make a one-click data set, and actually you could see in that little sample that there's this thing called boilerplate. All right, you can see it's a JSON document, right? This title and then the title of the site, for example. All right, so let's try this. Let's go into our scripts. Let's do a simple JSON key value extraction. So I'll pass it the StumbleUpon, and this is boilerplate, and this is title, and we'll execute it. And now we get an output data set. And we can see an example of what so it just extended it with this thing called boilerplate.title, sort of a dot notation, and you can see these are the titles, all right? So it went through all of the boilerplate and extracted those. Okay, so that works, but as I mentioned, it's just a complete hack, right? Because here's where it fails. Okay, so imagine I have a dictionary that looks more like this, where foo points to this somewhat more complicated structure. If I do the same thing, I keep the string to the right of the key, then I get that, right? Looks good so far. I follow the same formula. If it's a left brace, look for a right brace, et cetera, et cetera, et cetera. But what I end up with is I miss it, right? Because I get 2 left braces and 1 right brace because I was just looking for the first right brace and then I stopped. What I needed to do was count the number of left braces as I'm parsing the string left to right. And notice that when I found another left brace, that meant that later I needed to find 2 right braces. Okay, or if I happen to find 3 left braces, I need to find 3 right braces, right? So I need to find a balanced number of closing constructs, whether they be curly braces, square braces, or quotes, right? So this will fail horribly with somewhat more complicated JSON. And so what's happening here, right? Why is this so hard? Okay, and the explanation that is worth thinking about is that WisML, all right, is concerned with resources. It is about making workflows between sources and data sets and batch predictions and anomaly detections. It doesn't really have any knowledge. I mean, you can give it some knowledge about the contents of those resources in some cases. That's certainly valid to do. But by and large, it's interested in the big picture, right? Resources. Flatline is our second domain, or first domain-specific language we wrote, but we have 2 of them. But it is concerned only with data sets. The only thing it does is transform and filter data sets. That's it. Okay, so there's these little expressions, and you can use them to make new features, but that's it. It doesn't know what a data set is particularly. It doesn't know what the other resources are. It's very, very laser focused on that one task. All right, and if you continue to look at this, WisML is Turing complete, right? We already saw it's a full programming language. It's got data structures and iteration and conditional expressions. It's a complete programming language, whereas Flatline is not. Okay, it's very, very specific to take this feature, divide by 2, and multiply by this one. And the reason why these are different is because WisML is optimized for parallelization, right? It's got this big picture, and it knows, okay, I can do 10 models at a time, so I'll do that now. All right, whereas Flatline is optimized for speed. They're these little tiny transformations, or they don't have to be tiny, but they compile into something that executes on a data set and outputs a new data set, and they do that very, very quickly and very efficiently, right? Because you might have 1 billion rows in your data set, and you need that Flatline expression to be extremely fast, so it can be applied to all 1 billion rows. All right, so they're really meant for different things, and so I think that's valid to keep in mind as you're playing with WisML, and especially if you start trying to wrap Flatline expressions. That doesn't mean you can't do it. I haven't tried this, but just to give you a flavor of what would be involved, the problem is that we need the looping and the condition testing to be in the WisML side, right? Because that's what Flatline can't do, and we need Flatline to just do transformations and steps. And so we could actually do a much more elaborate JSON extraction by basically doing transformations one at a time. So we take our data set, we do the same split that we did before, and then we would just try it. We would try it with a left brace, one right brace, or 2 right braces, or 3 right braces, and we just keep building data sets until we get a balanced, right? So I actually had this idea where you could engineer a feature that says 0, there's no, -1 is not balanced yet, and greater than 0 is it's balanced. And then once you find it, because remember, it could be different for every row too. It might be that in row 3 you need 2 left or 2 right braces, but in row 20 you have a different JSON document and you need 4 right braces. So you actually have to just keep doing this until every single document has a balanced number of braces, and then you could use WisML to construct a giant flatline expression that knew exactly, but you're essentially building a feature inside your days that tells it for each row how many braces to use, and then you just run that last step, and boom, you're done. Of course, you probably wouldn't want to do this, right? I mean, this was just an exercise for me to experiment with what is possible and to kind of push the limits, and to have this really nice example of how WisML and Flatline can work together, but they're the fact that they are different, and to really highlight why they are different. Okay, and then the last thing I want to tell you about, I'm sure this came up before, but I just want to hammer it home. You may have saw, when we were building we were sort of doing this like rapid prototyping of the Redfin deals in the UI. It was really nice, right? Because we could just kind of click around and experiment. And then we had to make a WisML workflow, and we had to kind of break it down. And wouldn't it be nice if we could just take the result we had and say, build me a script? And that is something that we're working on. It's going to be called Reify. We actually have this in our command line tool called BigMLer. It reifies to Python, so you can point it at any resource, and it creates a Python script that repeats all of the steps. Every transformation, every feature engineering, every batch prediction, it doesn't matter. It builds a Python script that you can just run, and it repeats everything again. But we're going to do this in WisML, so you'll be able to just run a little script, an actual WisML script. So it's going to be WisML that builds WisML, and this will allow you to do that rapid prototyping in the UI, and then point a script at whatever you've built, and be able to have a WisML script as the output that repeats all of those steps.